All right, let's get started. Welcome, everyone. Thanks for joining. To those who are joining,
Sorry, I
uh,
also
all right,
started the Zoom recording.
recording. Yeah, it's okay. Uh, so, to those who are joining the seminar for the first time, please mute your audio. However, we encourage to keep your video on so that the speaker can see some faces. Please feel free to write the questions in the Zoom chat. Uh, if you'd like to ask the questions directly to the speaker, please do raise hand or mention it in the chat box. There will be two short 1 or 2 minutes breaks during the talk and 10-15 minutes Q&A session after the talk when you can unmute yourself and ask the questions directly. The slides are available in the upcoming seminars page. We'll also add it in the chat box in a moment. Uh, okay, so all right, so it's our pleasure to have Professor Amy Ward today. Amy is a professor of operations management at the University of Chicago Booth School of Business. She received her PhD from Stanford University in 2001. Her research focuses on approximation and control of stochastic systems with applications to the service industry. Prior to joining Booth, she was professor of data sciences and operations at the University of Southern California, Marshall School of Business. She has also been a visiting associate professor in Caltech CMS and an assistant professor at ISYE Georgia Tech. She recently was the chair of the Informs Applied Probability Society and the Service Management SIG chair for the MSOM Society, and she is currently the Stochastic Models co-area editor of the journal Operations Research. Today, she'll be talking about her recent work on behavior-aware queuing. Amy, welcome. Please go ahead.
Thank you very much. Good morning to everybody. And thank you very much to the organizers, Siva, Devenkar, Wena, and Christina. This is really appreciated that you're doing this. Today, I will talk on joint work with my co-authors, Raga and Yu Yang. Yu Yang is a Booth PhD student. And Raga and Yu Yang will be monitoring the chat throughout the talk to answer any questions and may help me with answering questions and discussion at the end. My goal here is to end after 50 minutes, so we do have some time for discussion. So we'll see how that goes. And so let me start by asking, what is a service operation and why do we care? So a service operation is an operation that produces value in a form other than a physical good. It's a business service such as consulting and banking. It's a trade service such as retail. It's a personal service such as restaurant or healthcare, public service such as government, infrastructure service such as transportation or communication. And this little picture of the toll booth will come back, so you can remind yourself of that. But why we care is that services accounted for over 70% of GDP in the US in 2019 Q4. And our focus in this talk is on the weighting part of services, so the queuing part. So I brought a little video. I know we all know what a queue looks like, but I thought maybe it's fun to see. And so the video you're looking at shows the weighting part of services, something with we're all familiar. I want the service, but I don't like the weighting. And so I want to think about how to design services in order to have as little weighting as possible, given the amount of resources in which I'm willing to invest. So why is there weighting? I know we know this in this audience, but just to emphasize, there's weighting because there's variability in when these people arrive, and there's variability in how long each of them takes at the server. Now, I can predict how that variability impacts system performance, and there's this wait time prediction formula. And the beauty of this formula is it's basically based on a two moment. So I need to know the mean service time and the mean inter-arrival time, and I need to know the coefficient of variation of the inter-arrival times of the service, coefficient of variation of the inter-arrival times and the service times. So that's really nice. It's something we teach to our MBA in our MBA operations class. And part of the beauty of the formula is it's very robust in the sense that it says, as utilization goes to 1, my wait time is going to increase exponentially. Now, there's a but coming up, And the but is that customers actually don't tend to wait forever. So a lot of queuing theory was developed thinking about inanimate jobs that will wait forever. Customers may not. And so in a service system, what you might see is instead of these wait times blowing up exponentially, you'll see yourself losing a lot of customers, which generally is not the goal. So this has been recognized. There was a foundational paper in late 60s, early 70s, and it basically suggests that the queue might operate like a finite buffer queue. So the idea is the customers come in, they have a value for the service, but they don't like to wait. They compare that, and if it doesn't come out right, they just don't come in at all. So that leads me to think about finite buffer queues. And at least in the Markovian setting, we have a different but known formula for what those predicted wait times will be. Now, if I'm thinking about a service system, it's not just the customers that are people, it is the servers that are people too. And that has consequences. So what I'm showing you is a graph. It's from a while ago. It's a toll booth. And the thing I want you to notice in the graph is that no matter how many lanes were open in that toll booth, if I look at the congestion, the time that a car was spinning at the booth is decreasing in the congestion. So in the queuing terminology, the service rate is decreasing as that row or your congestion level increases. And that's not something that's modeled in the formula I just showed you. So there's server behavior. And I kind of want to make the point that somehow that server behavior can affect system performance because I'm potentially seeing servers speed up here. Now, if you're not liking the toll booth context, let me give one other example of where this congestion impacts service rate in a setting that we're all familiar. So think academic refereeing. You in the audience are very good referees. You are fast, you get your reports in on time, and you give me nice reports. And so what happens? I ask you for more reports. And you might think about the fact that, well, maybe I should like pace myself because if I do this a little bit too quickly, all that happens is I just have more workload coming in. So there's this idea that maybe the congestion impacts the service rate. And of course, the service rate also impacts the waiting time. So that starts to lead us to thinking about some kind of equilibrium in the service rate. So rather than thinking about this service rate as an exogenous thing that I estimate from data, I want to think about it as an equilibrium that emerges endogenously. And this is sort of my motivation for doing that, and that's the theme of this talk. So my objective is we develop an analytical queuing model to investigate how server work speed is affected by design decisions concerning how many servers to staff and whether and when to turn away customers. So I'm doing this in the context of an NNNK, a finite buffer queuing model. I said something about customers being strategic, and the way that strategic behavior is evidencing itself, at least my assumption, is that it's evidencing itself as having a finite waiting room, so a finite buffer. So that's the last I'm going to say about customers being strategic, and we're just going to assume there's a finite buffer in play. And now I'm going to think about these servers being strategic. Well, not yet. The base model is I've got an arrival rate lambda, I have n servers, k is the buffer size, so k minus n is the waiting room size, and these n servers could be working at different rates. So there's a traditional queuing wait time formula. And what does it tell me? It tells me that the wait time in queue, this is expected steady state wait time in queue, should increase as the workload increases. And so by workload, I mean either the lambda or the k increases, because in either of those situations, I'm letting more customers come into the system, I'm giving the servers more work, or as the number of servers, my capacity decreases. That seems like a very, very natural rule of thumb. But think about the graph I just showed you. If servers speed up when they see more work, it's suddenly not obvious that this very common rule of thumb that the wait time increases as loading factor increases is going to work out. So when I think about behavior-aware queuing, what I really mean is that service rate is not going to remain fixed and exogenous. That service rate is going to be endogenous. It's going to depend on, I'll say, systemic design decisions. So like the N, the K, the arrival rate. And I don't actually know which way this is going to go. So as a consequence, commonly accepted rules of thumb can be wrong. For example, waiting time may not increase as workload increases. And so this is a consequence of the fact that in these service systems, we're really looking at humans, and the human behavior of potentially speeding up or slowing down matters. I think I defined workload, but workload is a little bit hard to define when I'm talking about the mu being endogenous, because I don't quite know if the servers are going to speed up or slow down as I increase the lambda or the K or the N. So if I say something like workload increases, I mean in your traditional queuing setting, when your mu's are fixed, if I increase lambda or K, or I decrease N, any of these is equivalent to increasing work, because I'm letting more customers come into the system. Okay, so let me talk about a little bit about a literature review so I can position what I'm going to do in the context of what's been seen. So empirical literature, the last DNA is a very nice survey paper talking about how workload impacts performance, impacts service rates. There are a couple papers I want to highlight. The papers I'm going to highlight, the Casey and Turwich and the Stats and Gino, they both show that servers can exhibit long-term fatigue effects. So what does that mean? If there's too much congestion in the system, the service rate will slow down. The Mass and Maradi paper evidences the opposite, that there is a social speed up effect. So those toll collectors, in field observations, they noticed that if there was congestion in the system, they actually served faster. They didn't chat with the people waiting. And so as a consequence, they served faster. So the speed up effect could come from the customers. It could also come from the servers. You look at your colleague's on fire, your colleague's working really hard, you want to too. And so these two effects, there's a little bit of a tension between, am I going to speed up because of congestion, or am I going to slow down because of congestion? And we would like to formulate a model that can predict what's going to happen, the speed up or the slowdown. We're going to be talking about an equilibrium service rate. So that puts me in the space of a queuing game. There is a lot of literature on customer behavior. We're focused more on the server side. So I'm referring you to the survey books and chapters for the customer side. It also surveys some of the server side. On the server side, I'm looking at situations where servers have decision-making power over their service rates. And I'm also looking at large system asymptotics, or I will be. And 4 papers that have those elements are the 4 I've listed. The closest being the Gopalakrishnan et al., because it has the same utility function as ours. However, the buffer size is infinite. So all of the customers are getting into the system. There's no way to regulate, say, which customers come in and which customers don't come in. The last paper is a bit of a shout out to those in the audience that are interested in machine learning. And I include it because it used queuing insights to improve machine learning predictions using a lasso method for an emergency room. And so I think if you want a grander vision or in your head or something a little bit more thought-provoking, is how do we use these analytical queuing models and the insights that come out of them? Can we use them to improve ML predictions? Okay, but that was a bit of a digression. That's the back of your mind thought. The talk outline for today, I'll talk about our model. Then I'm going to talk about the quote, easy single server setting, because even when there's one server, we see some interesting things coming out. Then the many server setting, then I'll talk about our asymptotic analysis. Okay, so I said something about our model, but I didn't exactly say how this endogenous service rate was going to work. So that's what I want to do. Quickly remind you, I've got the MMNK model. So arrival rates lambda, buffer size is K, or waiting room size is K minus N. I've got N servers, and I'm assuming a random routing. So if an arrival happens and there's more than one server free, I will just randomly flip a coin to decide which server gets the job. The main difference here is instead of these service rates being exogenous, I'm thinking the servers as being humans, and these service rates are going to emerge as an equilibrium. So the star denotes that that's an equilibrium. My concept is a Nash equilibrium service rate. So the servers want to choose rates mu1 through mu(n) that maximize their utility function. What is the utility function? The utility function incorporates idleness and a cost of effort. So the idleness, this II, this is the idleness that server I experiences when the vector of service rates is this mu vec. And it's the steady state expected fraction of time servers are idle as opposed to working to serve customers. The effort cost function, we assume it's continuous, differentiable, strictly increasing, and convex, and is normalized to C of 0 equals 0. I think the first bits, the strictly increasing and convex, is natural. As I speed up, I have to work harder. Also at the margin, I have to work harder. The normalization to C of 0 equals 0 is coming out with respect to an individual rationality condition. And I'll talk about that in just a minute. The cost functions are the same for all of the servers. So given that, it's sensible for me to think about symmetric equilibrium. That is what I'm going to do. And so what is this? This is U1 is I'm working at rate mu1 and everybody else is working at rate mu star. So if I want to get an equilibrium, the solution to this argmax needs to come out at mu1 equals mu star. And so this mu1 of mu1, so I'm working at mu1, here's me, I'm working at mu1, everybody else is working at rate mu. I need one tag server, it didn't have to be server 1, but that's convenient. I'm trading off idleness. So idleness, I'm working at mu1, everybody else is working at rate mu, and effort. This is a non-trivial trade-off because both are increasing in mu1. And the thing to think in the background is this is a volunteer or fixed wage service system, so there's no bonuses. So I value idleness, but there's a cost to working fast. If I work fast, I get more idleness, but it's a cost. And this C of 0 equals to 0, you can think about that as a normalization. So the normalization is if I don't work at all, I have 0 utility. That satisfies my individual rationality condition. If you want to model a fixed payment somewhere else that's, I don't know, M, then you can assume that your cost function is normalized so that C of 0, it's negative. But it doesn't make any impact in our analysis. It's strictly a normalization. Maybe it's also interesting to say that in contrast to the mean field gains in Bruce's talk last week, the jump rates of the underlying Markov process are constant over time. So the servers are choosing fixed rates, and they're basically answering the question of, do I want to work fast or do I want to work slow, given that I have a lot of peers or very few peers? How many agents am I sharing that work with? So I'm optimizing a utility function based on a steady state distribution. If I want to think about how this system performs, I need to know my mu star. I need to know my equilibrium service rate, assuming it exists. So that's what I want to focus on next, is I want to focus on how do I figure out how that mu star, well, when it exists, how it behaves. And if you think about the steps to look at an equilibrium, well, I need to know that it satisfies a first order condition. I need to know that there's non-negative utility so that I'm satisfying individual rationality. And I need to make sure that this argmax, this mu1, when it equals mu star, is indeed a global maximum. So those are my 3 sort of technical steps in trying to understand this mu star. I think this is a good time to pause for questions. I want to make sure the model is clear. Go? No questions?
There is one question in the chat box. Geeta? Why are the service rates same for each server?
That's a great question. So because I'm focusing on symmetric equilibrium, the service rates are the same for n-1 servers. And I have to figure out what this tag, whether or not this tag server, whether or not it will optimize this tag server's utility, maximize this tag server's utility, if this tag server also serves at rate mu. So in the background, I need a model where I can have different service rates. But what I'm looking for is when I solve for my equilibrium, I need to make sure that all of the servers working at this same service rate mu star are indeed maximizing their utility. And that means here, I need a function of mu1 comma mu star. So n-1 servers working at mu star, I'm working at mu1. And I hope that the solution to that, well, if the solution to that comes out mu1 equals mu star, then I will have a symmetric equilibrium. It's good?
Thank you.
Okay, so I'm going to go on. I said the first step is understanding first order conditions.
There is one more question, sorry. Why is the symmetric equilibrium interesting to look at from Sushil?
Oh, that's also a good question. I can give you a couple answers to that. The one is maybe a little bit of a non-answer in the sense that, well, the cost functions, everybody has the same cost function, so it seems reasonable to look at the symmetric equilibrium. Another answer I can give you is not in this work, but in work we're still working on in the background that Raga and Yu-Yang can talk about. If you look at the social optimum problem, the solution to the social optimum problem has all the servers working at the same service rate. And that's something we just figured out last week. So maybe that's a slightly more satisfying answer, even though in this talk, I'm not going to say anything about the social optimum versus this individual maximization problem. And the third thing to follow up on in there is we actually don't know if they're asymmetric equilibrium. There could be, it's not something we've focused on. But I suppose we're, yeah, is that good? I'm looking off to the side because the people I see are a little bit off to my side, whereas my slides are right in front of me.
Yeah, that's good. Thanks.
Okay, thank you very much. Okay, so then if I'm going to focus on the symmetric equilibrium and I want to think about the first order condition that I need to solve, so that's sort of step one. My first lemma writes out what that first order condition is. So I have m(k) system, arrival rate lambda, n-1 servers working at rate mu, and a tag server at rate mu1. This is the expression for the idle time. The row is lambda over mu, not lambda over n mu, as a lot of us are used to seeing. So that's the notation. The Erlang C, so I think a lot of you in the audience will be familiar with Erlang C. That's the probability, the steady state probability of delay in the infinite server system, infinite MMN system. And so you can see that I can write this idle time as a function of the Erlang C, a function of the Erlang C function. So that's nice. It's a little bit messy. And if you think about the first order condition, what do I need to solve? Well, a candidate equilibrium service rate solves partial of the idle time with respect to mu1, evaluated at mu1 equals mu, needs to equal C prime of mu. So this is my candidate equilibrium service rate in the sense that it solves the first order condition. I still need to check that it is indeed a global maximum, not a local maximum. And I need to check that there's a non-negative utility associated with it. So that's why it's candidate. But what you can see here is this is kind of messy, and I don't really have a hope of getting closed form expressions to this formula. I can say something, and what I can say is that the first order condition admits at least one solution if this condition is satisfied. One way to think about this condition is if I take a cost function of the form C of mu equals CE mu to the P. So if your P is greater than K minus N plus 1, that's condition A here, your limit here is going to be 0. So basically the condition is always satisfied. And you can think about it as it's a server resistance. It's an initial server resistance to going from the idle state to having to work. So I think that's one way to think about what this condition is. Otherwise, if the limit here is not 0, you're going to have to worry a little bit about your parameters, and that's our case B. But I think the nice thing is, okay, at least there's a sufficient condition for knowing that the first order condition admits at least one solution. We think it's a good sufficient condition in the sense that for the single server system, it's also necessary, but we can't explicitly say that for the mini server system. Right, so I'm starting to think about solutions to this first order condition. They're my candidate equilibrium. I want to know how the solutions behave. And if I want to start thinking about how the solutions behave, I'm going to start thinking about it in the quote easiest setting, which is the single server setting. So I'm doing that. I'm eliminating competition. I'm just focusing on what's happening when there's this one server and he's trying to maximize his utility. X-axis is K, Y-axis is the equilibrium service rate. I know equilibrium is a little bit degenerate with one server, but we'll go with it. And what you can see is that as K increases, so my workload increases. Lambda is 1, my service rate is increasing. So this is like what you saw in my data for the toll booth. More congestion, servers are working faster. Well, it's not quite that simple. So I start increasing lambda, and what happens? These dotted lines show you that I lose the equilibrium. So I have an equilibrium. I lose it at the dotted line. I lose it because the server is no longer able to attain positive utility. The effort to keep up with that loading factor is just too much. And I can explain that with a proposition. So there exists some K over bar that could be infinite, such that my equilibrium service rate is positive. It exists if and only if the K is less than or equal to K over bar. So you're seeing these K over bars at the dividing point between the straight line or the solid line and the dashed line. The K over bar equals infinity. So that's what you see in the blue curve with the lambda equals 1, if and only if this condition is satisfied. And if you look at these conditions, CE lambda to the P, well, it's saying something about how hard the server has to work versus how many arrivals are being let in. So it kind of makes sense that if this combination of how hard I have to work to clear out all my arrivals is reasonable, I should have an equilibrium. And if it exists, it's going to be unique. I can also give you a sufficient condition for when it's monotonic. And that sufficient condition is satisfied in all of the pictures you see in the graph. So at this point, you might be thinking, okay, well, that's nice. And then I'm going to show you this picture. And this picture says, oh, well, wow, okay, increasing and then decreasing. So the equilibrium service rates are not always monotonic. And what's happening in something like this? Well, it's increasing because congestion's happening. I'm feeling that social speed up pressure. And then if you overload me too much, I'm just fatigued. I'm going to slow down. And so that's what you're seeing here. And at some point, I lose the equilibrium. And again, I lose the equilibrium, my utility function becomes negative. So I was going to pause for questions on is the single server setting clear? I think just out of deference for time, I'm going to keep going and move and let the questions come out at the end. Okay? Okay. Okay, so I want to move now from the quote easy single server setting to the mini server setting. And let's think about what's going to be the main difference here. In the easy single server setting, there was no competitive effects in play. In the mini server setting, I have competitive effects in play. And what did you see in the single server setting that was interesting? You saw non-monotonicity. You saw non-monotonicity and you saw me losing equilibrium. So instead of me pausing for questions, I'm going to pause to ask you a question, which is just to think about in your head for a little bit before I move on, which is what do you expect to be different when we move from 1 to 2 servers, a setting in which we also have not completion, competition for idle time. So I'm going to pause. You're thinking in your head, what do you expect to be different? Okay, and now let's start talking about what's different. So 2 servers, x-axis is lambda, y-axis is k. Here's my effort cost function. And my contour plot shows when I have 1 equilibrium, more than 1 equilibrium, and no equilibrium. And if you paid attention to my single server plot, something that I didn't say but is actually happening is sometimes there's no local maximum and no equilibrium, and sometimes I have a local maximum, but it's not an equilibrium. So both of these effects are in play here. A new thing here is 1 equilibrium versus multiple equilibrium. So one new thing I've added one new thing that appears when we go from 1 server to 2 servers is that you may get more than 1 equilibrium. And I want to dive in a little bit more into what's happening and the intuition for what's happening. So a few more plots. So the plots I'm showing you here are basically all like the single server system. How are they like it? They're like it in the sense, x-axis is k. I'm using the same cost function. I've just gone from 1 to 2 servers. The blue is the mu star. So the blue is showing you the equilibrium service rate. The red is showing the utility function that is gained at that equilibrium service rate. So if the workload is increasing, if k is increasing, you should intuitively expect that the servers are getting less utility because they have to work harder. So that's true. That's true in all of the graphs, basically. I said it's like the single server setting in the sense that you're seeing the service rate can increase, it can decrease, and we can lose equilibrium. Okay, so we're feeling like, okay, well, that's nice. And now I'm going to show you this picture. And this one, we had to think about it a lot. So what's so interesting about this picture is, let's look at this blue line. I have an equilibrium service rate, I lose it, and then it comes back. So there's this interesting transition that is happening in this 2 server setting that never happens in the single server setting, which is here I have an equilibrium. And instead of going from having an equilibrium to not having an equilibrium, I actually go as the arrival rate increases from having an equilibrium always to having an equilibrium, it disappearing and then having it again, and it just disappearing forever. Now, why might that happen? Well, the reason it happens is that with 2 servers, if you look at the idle time, this I of mu1 comma mu function, it is basically always higher than the equivalent for the single server system, but not uniformly. And what I mean by not uniformly is that marginal increase in idle time when this k increases can actually be a big enough jump, a big enough bump, such that these servers are again getting positive utility. And so we found this effect pretty interesting. And this is definitely different than what you see in a single server setting. You were paying attention to my contour plot. You're thinking, well, there was something else I remember being different in the setting, and she hasn't even mentioned it. She showed me multiple equilibrium. Okay, so I've actually been hiding something from you. There can be multiple equilibrium, and you'll notice in 3 of these plots, there is a dotted blue line. The dotted blue line here is my slower equilibrium service rate. So I have a slower equilibrium service rate and a faster equilibrium service rate. And the way to think about that is either the servers are working faster, they have more effort cost, but they're getting more idle time, or they're choosing to work slower. And when they work slower, they're having lower effort cost, but less idle time. Why doesn't that happen in the single server setting? Well, it doesn't happen in the single server setting because it's just 1 server and he's going to go to the utility that is maximum for him. In the 2 server setting, I could have these multiple equilibriums. So that's happening from the competitive effect. But the utility associated with this faster service rate is higher. And we have an equilibrium selection theorem lurking in the background. But you can also notice that that's very nice from the system manager's point of view because he'd like the servers to work faster. And it's also nice from the server's point of view because they're getting more utility. Okay, but I want to think a little bit like this slower equilibrium disappears here, and it disappears when this fast equilibrium is still in play. And so this slower equilibrium disappears. So think about it. The servers are working harder. There's competitive effects. They have to work harder. And eventually they can't. Well, let's see what happens to the utility functions. So look at this K. This point here is around 7.2. So at 7.2, what's happening? The utility function is taking a nosedive. And I went ahead and I plotted, and this goes back to the question earlier in the talk. So I am plotting now, it's U, the utility, when all my other servers work at this candidate equilibrium service rate mu star question mark, and I'm the tag server mu1, and I'm trying to figure out what is my service rate that gives me maximum utility when everybody else is working at mu star question mark. So if K equals 7, this is my slower equilibrium. If K equals 7, I've got these two local maximums, but this one at mu star question mark gives me higher utility, so that's where I work at. At K equals 7.2, exactly when I lose the equilibrium, I'm getting the same utility at both of these local maximum. And at K equals 7.23, so I've now lost the equilibrium. Why did I lose it? I lost it because my local maximum at mu star question mark here is no longer a global maximum. The global maximum is over here. So I've lost my symmetric equilibrium. And the thing about these plots is I'm also kind of emphasizing to you that when I solve that first order condition, and we've had a sufficient condition for a solution to the first order condition, I still need to know that I'm going to have a global maximum to make sure that well, in addition to individual rationality, I need to know that I have a global maximum to make sure that it really is an equilibrium. And these plots should suggest to you that that is actually really hard to do. And the reason it's really hard to do is because I don't have one maximum. I've got two local maximums, and it's really hard to sort out which one is going to be larger. So is there any hope? I've shown you several different plots. They're numerics. I can show you some interesting phenomenon, but I'm a little bit unsatisfied because I'd like to show you something that gets a little bit more at structural results, that tells me a little bit more about the behavior of these equilibrium, that actually makes sure that my solution to the first order condition is an equilibrium. So we need to think a little bit. And let me show you some pictures to suggest that there is some hope. So same cost function. My buffer size is just going to be twice the number of servers. My plots are a little bit different though. The x-axis is lambda, the y-axis is mu star. And so what you should be thinking is I am graphing mu star of lambda here. So I'm changing lambda. And the service rate, the number of servers I staff is going to change dependent on lambda. And the number of servers I staff is changing dependent on lambda differently in each of the three graphs. So what do you see? Well, in the first graph, I always have two equilibrium, no matter how large lambda gets. In the second graph, I start out with two equilibrium. As lambda becomes large, they sort of become one. And in the third graph, the equilibria just seem to disappear for large lambda. So this is my answer, is that yes, it looks like there's some hope. There's some clear structure emerging in these graphs. And it suggests to us, what should we be doing? Well, it looks like an asymptotic regime in which the lambda gets large and the number of servers gets large at the same time will be helpful. So that means I'm thinking about an asymptotic regime that captures large service systems that are serving a large volume of customers. This isn't your mom and pop corner store. This is your national Whole Foods or something like that. So service systems that are serving a large amount of demand. And I'm saying this provides hope. So let me tell you exactly what my asymptotic analysis is going to do. Our asymptotic regime is one in which lambda becomes large. In this system, having a rival rate lambda, so I'm going to superscript everything with lambda to denote that that's the system that has a rival rate lambda. The n lambda is going to denote the staffing level. The k lambda greater than or equal to n lambda is the buffer size. And in this system having arrival rate lambda, staffing in lambda, and buffer size k lambda, the mu star question mark comma lambda denotes a solution to the FOC, and the mu star comma lambda denotes an equilibrium service rate. So notation's the same, I'm just adding that superscript lambda. And here's my FOC. So when you look at that FOC, your left-hand side has a lambda on it, your right-hand side doesn't. So that means if I want to understand solutions to the FOC, it seems that if I can get a handle on what the limit of the left-hand side is, I'm going to be in, hopefully, pretty good shape. So that's exactly what I'm going to try to do. So my first lemma is fix mu. And I'm going to look at this linear staffing. And if I look at this linear staffing and I look at the limit of the left-hand side of that first order condition, I have a sensible limit. Okay? And that limit looks pretty nice in the sense that you can imagine going this guy equals C prime of mu and solving that analytically. That should have a lot of analytic traction. The other thing I'm going to note in this lemma is if I staff either sublinearly or superlinearly, then this limit is just going to be 0. So it seems that the linear staffing is the right thing to do to capture some kind of non-trivial server behavior. If I staff sublinearly, the servers are just going to say, wow, you're overloading me with work. I'm not working. If I staff superlinearly, the servers are going to say, wow, there is so much help. I can just slow down to 0 and somebody else's, and we're still good. And so neither of these limits are particularly helpful. So I'm focusing on the linear staffing. So if I want to approximate a solution to the first order condition, it looks like I can focus on this linear staffing. And so instead of this on the right-hand side, I'm going to take the derivative of this guy. Or sorry, I'm going to, not the derivative of this guy. Instead of this on the right-hand side, instead of this on the left-hand side, I'm going to look at its limit and replace the left-hand side by its limit. And so here's my FOC. Here's my limiting FOC. I've replaced the left-hand side of the FOC with its limit. So let's look at this. This is now a pretty nice function. First of all, if I rearrange the terms, it's convex. So just done a little bit of algebra. Left-hand side here is a constant. Right-hand side is convex. So that means I should get 0, 1, or 2 solutions. Well, that's interesting because remember the pictures I showed you had 0, 1, or 2 solutions. And now I can also tell you that the way I chose that constant, the way I grew my n was not arbitrary. So for this particular cost function, I can solve this limiting FOC. We can, and I'm going to find that if the A is less than 0.75, I get 2 solutions. If the A is exactly 0.75, I get 1 solution. And if the A is greater than 0.75, I get no solutions. And that is reflected in these 3 graphs. So in one case, I chose an A less than 0.75. In one case, I chose an A exactly equal to 0.75. And in one case, I chose an A greater than 0.75. There's another interesting thing that's coming out of this limiting FOC, which is you might be asking yourself, how fast will servers ever work? And we can actually answer that because if you look at the maximum possible solution to this, so the maximum possible solution is going to satisfy mu max times C prime of mu max equals 1/4. That's the maximum possible mu I can ever get for any A. And what does this tell me and why am I pointing out? Well, notice the maximum service rate I can get is not dependent on my design decisions. It's not dependent on how many servers I staff, and it's not dependent on K. It's dependent purely on the ability or the effort of that server. And I think that makes sense. So what you're thinking about is given that this is going to control the maximum effort the servers can work at, as a system manager, you may want to be thinking, how do you choose your N and your K to draw that out? I'm not going to talk about it in this talk, but I think it's clear that that's a question that's sort of lurking. Now, from these pictures, I haven't given you a theorem, but the pictures suggest that somehow this limiting FOC should be able to tell me something about equilibrium. And that's the next thing I'm going to do. I want to make one more observation before I do that, and that's if I look at this limiting FOC, any positive solution is going to have mu greater than A, because this left-hand side, that's a positive part. So to get a positive solution, I have to have mu greater than A. If that's the case, then if I look back into my prelimit and I look at this loading factor under any candidate equilibrium service rate is going to be less than 1. So that suggests that this asymptotic regime that I'm looking at and this limiting FOC that I'm looking at is picking off what I'll call stable equilibrium. And they're stable in the sense that if I didn't have the K, the servers are working fast enough to keep the system stable. So I've got a limiting FOC that is picking off, I'll call them, quote, stable candidate equilibrium. With that in mind, the theorem I have that connects the sort of pictures I showed you, earlier, rigorously connects them to this limiting FOC, is the following holds for all large enough lambda. If A is such that I have 2 service rates that solve the limiting FOC, then the prelim FOC has 2 solutions in A infinity. So it has 2 stable candidate equilibrium. It may also have an unstable one, but it has 2 stable ones. If A greater than 0 is such that no mu solves this limiting FOC, then I will have no stable equilibrium in A infinity. No stable candidate equilibrium, so no solution. The FOC has no solution in A infinity. And if the A is such that I have exactly 1 mu that solves the limiting FOC, then either I have 2 solutions or no solutions, and that depends on my second order terms. The furthermore is just to emphasize that for any epsilon greater than 0, if there exists at least 1 solution to this limiting FOC, then there exists a mu lambda that solves the FOC and is arbitrarily close to that solution. So there is indeed an explicit connection between something that solves this limiting FOC and something that solves this FOC. That still only talked about solutions to the first order condition. And remember, I showed you these plots where I had this multiple local maximum, and I said, actually it's kind of hard in these systems to figure out which of these local maximum is a global maximum. But in this limit regime, I can do that. And so one thing that's really nice is it's not just these candidate equilibrium, they're not just candidate equilibrium, they're also actually equilibrium. And how do I know that? So the first lemma is for large enough lambda when A is less than mu, the second partial derivative of that idle time is less than 0. So that means my utility function is going to be concave. So that means if I have a solution to the FOC and it has non-negative utility, I know from that lemma that it's going to be an equilibrium. And so my corollary is for all large enough lambda, mu star lambda greater than 0 is an equilibrium if and only if mu star lambda satisfies the first order condition. And that's really nice because that was not something that was easy to get at given those 2 local maximum that I showed you earlier. A couple open questions that I want to mention. You may have noticed that K actually has not come into play here. So one open question is, can we develop a limiting regime that preserves the impact of the K? What we've done right now is, I'll call it, we characterize first order impact. And first order impact is whether or not these equilibrium are going to correspond to a stable system when I have an infinite buffer. So I'm sort of getting this first order characterization that's coming from this stability. But it seems like it'd be nice to sort of have some kind of second order characterization or something else in the limit regime that helps us understand the impact of this K. The other interesting open question is, can we develop a limiting regime that helps us to characterize unstable equilibrium? And here I can give you some very specific background. If you look at a loss system, so if your K equals in the prelimit, we can prove, and that's in the paper, that there always exists an equilibrium. So what's happening in this limit regime in the loss system, Well, there always exists an equilibrium, but that equilibrium mu star lambda is going to 0, which means the system is becoming unstable. And the only reason I have a positive recurrent process is because I have that K going on there. And somehow I'm not quite picking out those unstable equilibrium. So that's another open question that, open question there. Okay, so looking ahead, we're at the part in the talk where I've kind of done a fair bit with these equilibrium service rates for finite buffers. And if I circle all the way back around to the beginning of the talk, I said the motivation of having a finite buffer was because there's some of this foundational work that shows me a finite buffer is really tied to strategic arrivals. So I want to come around back to the beginning of the talk because I'm hoping that this work is providing a foundational analysis so that we can also look at interactions between strategic arrivals and servers. So let me say briefly how that happens. So the customer equilibrium that I sort of alluded to, but just said, oh, it's a finite buffer. How is that actually happening? So on the customer side, a customer who arrives to find I customers in the system, so this is a visible queue, the customer can see the customers in line, will join if and only if the value for service is greater than the cost of waiting. So the result is that a customer equilibrium strategy is to join if and only if there are no more than K star -1 customers in the system. And K star is defined by this value for service versus cost of waiting, the number of servers in the system, and the service rate. So this tells me that if I want to look at joint equilibrium, I have a natural definition for a joint equilibrium. My joint equilibrium is going to be K star mu star is a Nash equilibrium if and only if K star satisfies the condition I just showed you, except with mu star, the equilibrium service rate. And the equilibrium service rate is utility maximizing for each of the servers in the sense that we defined at the beginning of the talk. So we haven't done anything here. We think there's some interesting things to think about. And there's one really nice paper, it's restricted to the n=1 setting, but it shows you that there's some really interesting things that happen. And in particular, they, Chung, On, and Ryder has some nice benefit of anarchy results. So that's all I'm going to say about that. And I'm going to go on. I'm just at a little over 50 minutes, so I will go on to the summary here. There's a paper, so we also provided a paper link. Okay, so we studied mini strategic server finite buffer queuing system. We saw that equilibrium may or may not exist. That has consequences for system design because if you want to do prediction, you need to know what that equilibrium service rate is. When n=1 with a single server, we've got reasonably explicit conditions for the existence and for when your service rate is going to be monotonically increasing in the buffer size. When n is greater than 1, what we saw is that solving the FOC is difficult, and even when we can, guaranteeing an FOC solution is an equilibrium is hard. Fortunately, asymptotic analysis allows us to characterize when stable equilibria do and do not exist for systems with large arrival rate, so large demand, high volume. And if I want to think in with some sort of grand vision questions for the work, there's a survey paper that I cited in my lit review, and one of the things they observed is a noticeable disconnect between the work of queuing behavioralists equipped mostly with empirical tools and queuing theorists equipped with formal modeling tools. So we're hopeful that this helps bridge that disconnect. And the idea is if empiricists are seeing things like server fatigue, server slowdown, or server speed up, maybe we can develop models to predict that kind of behavior. The other grand vision question is, how do we better lessen the disconnect in the sense that we really need to go all the way back and close the loop and calibrate the model with data? But we don't know really what the right utility functions are to use to capture this server behavior. Right now, we're basically going on some things we've seen in the literature that this trade-off between idleness and effort is kind of reasonable for volunteer and fixed wage systems. But that's also kind of a grand vision question, and how do we sort of finally close the loop here? Okay, so this is where I am, and I think this is a great time to ask for any questions, and thank you very much.
Let's thank the speaker. So there has been a lot of discussions in the Zoom chat. So if you have any questions, please mention in the chat box or raise hand, and you can unmute yourself and directly ask the questions. Let's wait.
So I have a question. Hi, I'm Sushil. In the last part, you said that the valuation of a customer is R, which is a constant, but wouldn't it be more realistic to consider like a random valuation, because then each customer can have a different valuation? And if you
I think that's totally fair, and there are many papers that did that. What I gave you was exactly the model in the Knorr paper, which was a single server, and the Knudsen paper, which was a mini server. But absolutely, there are many different variations on how you want to do the customer behavior.
So in that case, would it be like interesting to see that case, and then if something interesting can happen? Because then the K won't be a constant here, because then it will be a random variable again.
Yeah, so I agree that that's interesting in terms of thinking about the interactions. It seems a little bit easier to move forward with a K that's a constant, but that doesn't mean that that's sort of the best way to do it, or that it's not more important to model some of the heterogeneity that you're alluding to in how customers value the service.
Okay, thanks.
Okay, so there is a lineup for questions. Alan, please go ahead.
Hey, Amy, thanks for the talk. You talk about asymptotic analysis. Do you have any idea about when that would start to kick in as far as lambda or K or N?
Yeah, that's a really good question. I'm going to go off and say hundreds of customers an hour, something like that. But it's kind of a gut feel. And actually, Raga and Yu Yang, you may have more of a sense from some of the numerics. Okay, so I think that the answer is we haven't thought too much about that convergence rate question you're asking.
Sorry, can you repeat the question? I was responding to some other comments in the chat and was distracted.
I was just wondering if you had any idea about, because the latter part of the talk relies on asymptotic analysis,
yeah,
when you might think that analysis would start to kick in as far as lambda or N?
Right. So as far as N, I think it's a 1 over square root N. It's very much a conjecture at this point. We just recently derived a bound on the derivative of the idle time that's independent of the scaling. So that bound comes out to be the limiting idle time minus like 1 over square root N. It could be faster than that, but yeah.
Thank you.
Okay, so next, Shane, please go ahead.
I guess Raga answered my question already, but I was curious, Amy. So thanks very much. I mean, the complexity of the equilibria here makes me sort of shudder to think about trying to use, a framework like this to design anything. And so I would love to have additional incentives for servers or some other tricks to induce better behavior that then means that we actually can move towards design. Raga says you're working on that?
Yeah, so this is clearly one specific utility function. And the utility function I said is only characterizing stable equilibria, but you can sort of imagine if you give servers some bonus, maybe payment bonus or something else, they might be much willing to work harder for you. So one of the things we're working on in terms of the design decision is expanding the scope of the utility functions, being able to get sort of a larger characterization of what these limiting regimes could be, and then trying to figure out, well, what design decisions should you make on, say, the N or the K such that you live in your desired regime? And right now, of course, we can't fully answer that question because we're really only characterizing the stable equilibria, which is kind of making sure the servers have some idle time.
Right. Thank you. And sorry, I'm going to sneak in one more question just because I've got the mic. Why is it that we don't currently have chaos in civilization because we're not taking into account these results?
That might be a little bit more deep philosophically that I can answer. But we started, I think one thing that's made me a little bit uncomfortable and sort of where this work has started is, I love queuing theory and I love queuing formula. They're like amazing to me. But there are some insights from them that the empiricists have kind of have shown are not holding up in certain situations. So I would say this is, I view it as kind of a first cut philosophically for how do we improve our models so that at least what we're predicting is not in contrast to what we're seeing when empiricists look at server behavior.
Thank you. That makes good sense.
Okay, next is Harsha, I think.
Hey, hi, Amy. Thank you for the talk. Very interesting. I had a question about the very last thing that you said, which was how do we better lessen such disconnect by doing model calibration? So I'm just curious what you have in mind there.
So I probably haven't thought about this carefully enough to give a particularly good answer. So let me say what the problem is. And then the hope is that I inspire people in the audience to help figure out solutions. The problem is that if you give me a data set right now, and you give me a data set, let's say of the toll booth, and I measure my service times and I measure my arrival times, what I might be able to do is if I just assume exogenous service rate and exogenous arrival rate, I might see that my predictions aren't quite matching because the servers were actually having this response to congestion. So at one congestion level, my prediction might work, but then it's not going to show that that my waiting times are sort of changing according to this congestion level. Now, what I don't know how to do is if I show the model that I just gave you, how do I take that data set and calibrate my utility function to that particular data set and make sure that the predictions coming out of that data set are matching the predictions coming out of my model? So I haven't quite closed that loop. And one of the reasons I haven't quite closed that loop is I don't know for sure what the best utility function is to model the human behavior at kind of a more detailed level. So right now I'm kind of grasping a little bit at like, okay, my model can predict some stuff that is like, here's where you might have some server speed up, here's where you might have some server slowdown. And I am using that in a steady state framework, not a transient framework. So that's another discussion. However, I can't fully calibrate from the data set to my predictions. And I think that's something that we kind of have in the back of our mind. But the best ways to approach that, still fumbling. Okay. Did that answer your question?
To some extent, yeah. Thank you.
Okay, so Ran, is your question already answered?
Yes, it was answered in the chat.
Okay. So Sushil, you said you have a quick question, clarification question.
Yeah, like digressing a little bit from the discussion we are having, but I was just a bit confused when you showed the graph of the utility and showed like two local minimums for different values of K.
Here?
This one, yeah. So what does it mean to have fractional values of K? Is it like a asymptotic regime already or
That's a very good question. I didn't say anything about it. The function is defined for fractional values of K. I suppose what you might think about is if you had some kind of randomized policy that half of the time let somebody in when the buffer size was 6, and half of the time let somebody in when it was 7, you might come out with this fractional value of k in some averaging sense. But this is just sort of noticing the fact that the functions we're working with are actually continuous in k, so we'll just show you the graph like that.
Oh, okay, thank you.
Potentially a little unsaturated, yeah.
So next is Weena. Is your question answered already?
Partially, so maybe I can just quickly ask.
Sorry, man, it's just one more to Sushil's question. One of the things that when you're starting to think about the joint equilibrium and what makes it hard is you really have to worry about that fractional value of k, because the customer equilibrium, you want to be an integer value. Yeah, okay, sorry, Weena?
Yeah, so so I was wondering, like, what would happen if we put a constraint on the dropping probability? Like we wanted to make sure the dropping probability is no larger than something, and would that help regulate the equilibrium behavior? But this question was answered in the chat box, saying like in the asymptotic regime you are considering, the blocking probability is always 0. But would it make sense to consider a regime where it's low but it's not always 0? And would that be interesting?
Yeah, actually, I'd like to follow on because you're asking a fantastic question. And I think if you think about system design questions and you think about a traditional queuing system and you think about something like minimize cost subject to dropping probability is no more than this amount, you know that in the constraint, the dropping probability is going to be increasing as lambda or k increases or as n decreases, right? So when I think about solving that optimization problem, there's a monotonicity I can use that helps me. Now, if I think about that optimization problem when the service rates are endogenous, I don't actually know, right? That dropping probability, it may or may not be increasing as the k increases.
Right,
and so suddenly that makes that entire problem, I think, potentially quite more interesting.
Oh.
And now your question is getting at what is the, I'd rather not use the word flaw. What is our asymptotic regime missing? What is missing in our asymptotic regime is I can't give you it's not going to capture an answer to how do I solve that particular design problem. I can only flag for you that it suggests that when I incorporate these behavioral elements, there's a lot of these system design problems that lose their monotonicity. And because they lose that monotonicity, it makes it a little bit more challenging to understand where that answer is going to be.
I see. Yeah, very interesting. Yeah. Okay, thank you.
So adding on to that point, maybe it would be interesting to look at non-symmetric equilibriums to make sure the dropping probability is low, more richer class of equilibrium.
It's a fair point. I'm going to hand it over to Raga and Yu Yang because they've done at least a little bit of numerical looking for asymmetric equilibrium, and I think it was in the case where it was an infinite buffer. And Raga, correct me if I'm wrong, but I don't think you saw any asymmetric equilibrium.
I don't think I looked for it actually in under random routing. We did look at.
You looked for it under different routing policies.
Equilibria for like fastest server first and slowest server first. So there they do exist, but I'm not sure for random.
Okay, so I think the answer is that we don't have an answer, but it is something that's kind of in the back of our minds. At least numerically, we could start searching for asymmetric equilibrium and see if there's anything interesting to work on there.
So next in line is Geeta, if it is not already answered in the chat box. Okay, so Vijay, is it answered there?
Oh, thanks, Divankar. I mean, I was just asking in terms of I think Raga sort of answered my question too, but if you're generally looking at humans and trying to model them, if you don't include behavioral aspects, it seems a little removed from reality. So why would you expect fully rational behavior? And similarly, in the data that you have, why would you expect the preferences to be rational? Wouldn't you? So you may not get a utility function that will map the correspond to what you see the servers are doing.
I'm
It's
smiling.
More a comment than anything else.
Yeah, I'm smiling because no, I don't necessarily expect to see rational behavior. I think that's, yeah, we don't always act rationally for sure. The way I would advance the model to you from the perspective of that point is that it's just kind of a starting phase of like seeing that like, okay, if we know that there's some effects that the traditional queuing models that assume customers will wait forever and servers never change their service rates don't quite capture. Now we want to start exploring models that incorporate that behavior. And to your point, there are better and worse ways to incorporate that behavior. And I don't think I know what the best ways are. I don't think we've done enough exploring to really fully understand that and fully understand what's the impact of the rationality assumption. Is that reasonable? Can I just not make it at all? I don't know, but these are still like sort of very new ways to think about the, well, maybe that's too much to say. I shouldn't say they're new ways to think about the modeling. I should say that we're still exploring that side of the behavioral aspect of queuing theory and capturing that in an analytic formula. So I guess that was a long way of saying there's a lot more to do here.
No, thank you. I mean, one suggestion maybe to look at is the K-level bounded rationality, where you don't assume fully rational, but you assume there's some basically certain, you go up to a certain level of the rationalizability type discussion, which may make sense in practice because you only get to see some limited information about the other servers. So.
Yeah, I think that's a good idea. I mean, we've sort of maybe informally mentioned bounded rationality amongst ourselves, but we've never followed up on anything.
And that might also be more tractable and that class of equilibrium might, calling them equilibria as questionable, might emerge more naturally than rational equilibrium.
Ah. Yeah, I hadn't thought about that. Thank you.
Okay, so Sunil, you can go ahead if you have a question. It is not answered.
Yeah, no, it's been answered by Raga. Thank you.
Okay, so is there any other question? Okay, so if there is no further question, then let's thank the speaker once again. Okay, so next week we have Mariana Olvera Cravioto from UNC Chapel Hill as the speaker, and we look forward to seeing you next week. Thank you all. Thank you all for being here.
Thank you.